This video is how to convert the imaginary roots that you normally get, the complex exponentials you normally get, into the nice exponentials times sines and cosines that we use to solve the initial value problems. So if you're okay just using the formula, that's fine, but if you're a little curious on how we turn this thing c1 e to the lambda plus mu ix plus c2 e to the lambda minus mu ix into sines and cosines and exponentials, that's what this video is about. So let's go ahead and jump in. So we have this difference equation we've been working with. I'm telling you it has imaginary roots, and I'm telling you the roots of the characteristic polynomial are lambda plus mu times I. And right, normally if we went with our guess, we would have y of x equals c1 times e to one of the roots, lambda plus mu I times x, plus c2 times e to the other root, lambda minus mu I times x. But that's, it's not very nice looking. We expected a real answer. Our problem looks pretty real. So there's an idea that you have to use and a trick. So the idea is we're going to simplify using this formula, e to the I theta equals cosine theta plus I sine theta. And you're going to have to trust me on that one. But let's go ahead and dive in. So how is this going to help us? Well, let's go ahead and do it for our own here. So if I write this a little differently, it's going to be, I can pull out a lambda x out of everything. So e to the lambda x. And I've got c1 e to the, I'm going to write this as mu x times I plus c2 e to the negative mu x times I. So e to the lambda x, that's kind of close to what we want, but we still have these complex exponentials in here. We want to try and get rid of those. So here's the idea. So we have e to the mu xi. Well, using this formula, that's going to be cosine of mu times x plus I sine of mu times x. All right, well, what about then e to the negative mu xi? Okay, that ends up being cosine of, instead of positive mu xi, we now have negative mu xi. So I just put the negative mu x inside the cosine, and I have plus I times sine of negative mu x. But I do want to simplify that a little. So the first thing is cosine is it's a symmetric function. So if you do cosine of negative a value, it's the same thing as cosine of positive that value. Right? You flip it about the y-axis, you get the same graph. So cosine of negative mu x is the same thing as cosine of positive mu x. But then for sine, and I do want to leave that plus off for a sec, sine is the opposite of cosine. So if you flip it about the y-axis, the y-axis with this negative, or x-axis, it ends up negating sine. So you actually have I sine of positive mu x, and you put a negative here, so those are the same. Essentially the negative can come out of the sine. So these two formulas, we want to work with those. So now the first clever trick is, okay, well, what if I take e to the mu x times I, and I add it to e to the negative mu x times I? Okay, well, that will end up being, I have cosine of positive mu x times cosine of mu x. Sorry, cosine of mu x plus cosine mu x, that's 2 cosine mu x. But here I have positive I sine mu x, and I add that to negative I sine mu x. So you actually end up with just 0 I sine mu x. Right, and if I want, I could actually take this and I could divide both sides by 2, and I could get e to the mu xi plus e to the negative mu xi over 2 is just cosine of mu x. Then kind of similarly, let me just draw this here. If I do e to the mu xi instead minus e to the negative mu xi, all right, well, that ends up being, I get cosine of mu x minus cosine mu x, so I get 0 cosines of mu x. But then I have I sine of mu x, and I subtract from that negative I sine mu x. So you end up with actually 2 I sine mu x plus 2 I sine mu x. And then if we divide both sides by 2i, we have e to the mu xi minus e to the negative mu xi over 2i equals sine of mu x. All right, and now for another clever trick. So we have our solution here. We have y of x. Let me just put in one more there. Y of x equals e to the lambda x times c1 e to the mu xi plus c2 e to the negative mu xi. And that's kind of similar to what we did, but we don't know that c1 and c2 are exactly equal to each other, we don't know they're equal and opposite, and they're not over 2. So it's a little hard to figure out how to do that, but we can pick new constants. Right, this is a very convenient thing to do, right? C1 and C2, that's nice. Well, what if we wrote it in a really weird way? So you could also write this as y of x equals e to the lambda x. I'm going to write c1, and I'm now going to have a c1 hat, so it's not the same thing as c1. I still want to use c1, it's c1 hat, over 2 plus c2 hat over 2i. And that's all times e to the mu xi. And then I'm going to have plus c2 now. I'm going to exchange it with something not as nice, but will amazingly kind of simplify itself. It's going to be c1 hat over 2 minus c2 hat over 2i times e to the negative mu xi. And then close parentheses for the e to the lambda x. So we can do that. C1 and C2 might be really complicated to solve for if we knew C1 and regular C2. But right, C1 hat, C2 hat, we have a plus here, we have a minus here. Whatever value C1 has and C2 has, we can pick C1 hat and C2 hat so that we get the same value. So this is all right to do. It's a really weird thing to do, but it is all right. But now the nice thing is if we actually separate this into C1 hat and C2 hat, we get these nice formulas that we can use to get rid of all the i's. So this is the same as e to the lambda x. Here I'm going to have C1 hat. So I have a C1 hat times a half times e to the mu xi, but I also have a C1 hat times 1/2 times e to the negative mu xi. So if we actually split all those up and recombine the terms, this is e to the mu xi plus e to the negative mu xi over 2. Right, I had the 1/2 times the e to the mu xi, I have the 1/2 times the e to the negative mu xi, I put them together in one fraction, I have, both of them. So this is, a really weird thing to do this exchange of constants, but it's going to work out to be something clever. And same thing we're going to do with the C2 hat. We're going to group those terms together. So here I have a C2 hat over 2i times e to the mu xi. So I have e to the mu xi, and it's over 2i. But over here I have a minus C2 hat over 2i times e to the negative mu xi. So that's the minus e to the negative mu xi over 2i. But that ends up simplifying to e to the lambda x, and I think I want one more line, so I'm going to scrunch it up a little. E to the lambda x, e to the mu xi plus e to the negative mu xi over 2 is actually cosine of mu x. So I can actually write this as c1 hat cosine of mu x. And e to the mu xi minus e to the negative mu xi over 2i, well, that's just sine of mu times x. So I can write this as plus c2 hat sine of mu x. So kind of everything resolved itself all at once. And then if I just multiply the e to the lambda x through, I get c1 hat e to the lambda x cosine of mu x plus c2 hat e to the lambda x times sine of mu x. So right, that was all thanks to this formula, e to the I theta equals cosine theta plus I sine theta. These clever tricks to add together the positive and negative complex exponential to just get cosine and just get sine. And then the really clever trick to rewrite the constants we started with, C1 and C2, into these really weird combination of constants, C1 hat and C2 hat in both of these. And then by going back and you kind of group everything by C1 hat and C2 hat, you get this fraction that we ended up wanting that actually simplifies to cosine mu x. And here on C2 hat, you got a fraction that ended up simplifying to sine of mu x. So that's how it works, in case you were curious. But again, if you really want to, you can just follow the formula each time.